Hi again, everybody, and welcome back. This example 8.9, is a great first example of the use of conservation of energy to solve for some kinematic values like velocity and so forth. This type of problem right here, it's a modified Atwood machine, and you might be ready to draw all kinds of forces in on this that are causing it to move. We have this Atwood machine, and we're told that there is friction between this mass and the, oops, I didn't mean to draw on that, between this mass here and the surface. So friction would be an opposing force, that is a force that's opposing the hanging mass force right here. But let's just hold off on drawing forces in here for a second and see if we can make some sense of this system just using conservation of energy. All right, before I get into that, let's write down all of our nodes first, okay? So the mass of the mass 1 equals 2.40 kilograms, and mass 2 equals 1.80 kilograms. Okay, got it? They move through a distance. The D equals, a better equals sign there. D equals 0.500 meters. Okay, half a meter. And we're also told that the coefficient of kinetic friction equals 0.450, and then that's it. There's no units. It's just 0.450. What we want to find out is what is the speed of the blocks just before M2 hits the ground. All right, so final velocity of the system is what we're solving for right there. Now again, you may be prone to want to start drawing in forces and stuff, and if so, it probably means you were paying attention during those chapters, and that's good. But there may be an easier way to do this, and that is using conservation of energy. Just as a quick reminder, oh, by the way, let's see here, I'm going to shrink this down so we have a little more space. As a quick reminder for conservation of energy. Conservation of energy, if all energy is conserved, then we say that energy, oh darn, I'm writing a sigma, that's not an E. Energy final equals energy initial. It could be in different forms. It could be a lot of kinetic energy and a little bit of potential, or a lot of potential and a little bit of kinetic, or some combination of both. But if we're talking about non-conservative work, then that means that the difference in final system energy and the initial system energy is accounted for by some non-conservative work that is done. This non-conservative work that's going to be done is going to be done by friction. Friction acting through this 0.500 meter distance that the system falls through. Okay? So, let's take these statements about final and initial system energy, and let's break them into their various different components. All right, final energy, final system energy is going to be kinetic final plus, you know what, I'm going to draw this a little bit lower right here. It may not make sense right now, but it will in a second. Kinetic final plus potential final equals kinetic initial plus potential initial plus any non-conservative work that is done. In this case, it's going to be by friction. By the way, just as a reminder, I always put a plus in front of the non-conservative work. If friction happens to be negative, then I put a negative in there, and it winds up kind of being subtracted. But I don't like putting a minus sign out front, because sometimes that might lead to doubling up on your minus signs and then getting a wrong answer. Okay, so I think we all know that friction is going to be creating negative work, or doing negative work on the system. So we'll put a negative in there, but I'm putting a plus sign out front for now. Okay, so let's see if we can write these in a little bit more detail. All right, kinetic final. Now this is of the system, of the entire system. For the system, here, that'll fill that spot right there. What's kinetic final? Well, that is 1/2 m of the system times velocity of the system final. You know what? I'm going to put m cis, but the velocity, I think we all assume that means the whole system. Just the velocity final squared, right? Kinetic energy is 1/2 mv squared. This is just a reminder that it's the whole system mass, not just the one of the masses. All right, potential energy plus the potential energy final right here. Well, when this M2 hits the ground, it has nowhere else to fall. The falling action of this M2 is really what is causing the system to move. Yes, M1 is starting some distance above the ground, but it's not moving through that distance at all, so it's not doing any work. It's not adding any energy to the system. All the energy to the system is being created by this falling mass 2 right there. So that means that when it hits the ground, or right before it, right as it hits the ground, that means M cis G H. If that H is 0, it drops down to 0, then that means the final potential energy is 0. Okay? So that's our final right there. What I'm going to do is I'm going to put an equal sign here, and then I'm going to run out of space if I don't go to the next line. So I'm going to account for the initial energy of the system right here. Okay? So the initial energy of the system is 1/2 mass of the system times initial velocity squared, right? 1/2 mv squared. Now wait a minute. This is released from what? It's released from rest, right? And we know that release from rest means that the initial velocity is 0, so that's nice. That'll go away too in just a second, but we're just accounting for it right now. All right? And what is the initial potential energy? Well, the initial potential energy is, and here's where we need to be careful, it's the energy of just this falling block. This, the potential energy of this isn't doing anything to add to the system. Only this is right here. So we're going to say mgh, but we need to be specific. That's going to be mass 2 times gravity falling through that height right there. All right? In that case, the height is that distance d that that the block slides through horizontally up here. Okay, so h and d are going to be the same thing because the whole system moves the same distance. Okay. Plus now, and I think I can fit this all on one line, the non-conservative work that is done. Well, what's creating the non-conservative work right here? Kinetic friction is, isn't it? Kinetic friction is. It's always acting against the direction of motion. So we're going to say that that is mu k times mg. Oh, I should say, m what? Which mass is creating that friction? Both masses? No, just m1, right? m1 times gravity. So there's our mu k, there's our normal force. And that friction force that's acting against the system right there, Fk, is doing that for what distance? For a distance d. Okay? So this accounts for that non-conservative work that is done. So we have mu k times our normal force, m1g, times our distance. And then, of course, we always multiply with forces. We multiply by the cosine of the angle between the direction of motion and the force. In this case, the direction of motion and the force, like with all friction, is 180. So the cosine of 180 means that we put a minus sign in front. And, of course, that's our proof that friction does negative work. Okay? So, like I said, I always put a plus sign up front, but if it's negative work, the minus sign goes in there, and then it ultimately gets subtracted. Okay? So I think we can make this a little bit easier. We're solving for what? Let me circle this in green right there. Final velocity squared. We want to solve for that. So let's see if we can clean this up a little bit and solve for that. So it's going to be 1/2 mass of the system times final velocity squared plus that equals 0 and that equals 0. So equals mass 2 times g times h. That's the potential energy that's causing the system to move. Plus this negative mu k m1g. It looks like mig m1g times the distance. This right here accounts for the negative work done by friction. Okay, I think we can solve for the final velocity. Final velocity of the system. What I'm going to do is, let's see. Well, I'm going to multiply. I'm going to take this 2 right here and multiply it up. So it's going to be 2 mgh plus 2 times all this stuff right here. And then I'm going to divide by mass of the system. All right, V final equals 2 mgh. In fact, you know what? I'm even going to put the 2 out front. 2 times, let's see, parentheses, mass 2gh plus negative mu k mass 1g times distance, which remember that d and the h are the same thing. I could probably just put h in there or d. This seems more like an h for height. This seems more like a distance for d because it's horizontal, but remember they are the same thing. That height and that distance the horizontal block moves are the same thing. So we're going to put the same value in there. And then let's see. Oh, we have to divide by mass of the system right here, right? So I'm going to put that down below like so. I'll close the parentheses. Mass of the system, which of course is mass 1 plus mass 2. The last thing I needed to do was take this VF squared and square root it to get regular VF, which means I need to square root the other side as well. Like so. And this is going to solve for the final velocity of our system. All right, we didn't really mark any forces on here. Well, okay, I wrote that kinetic friction right there, but we didn't use forces to find the net force in the system and then the net work on the system. No, we used conservation of energy. Okay, so square root of, I'm afraid I might just run out of some space here, but maybe I can squeeze it all in. 2 times, what's the mass 2? That is 1.8, right? 1.8, not 1.0. 1.8, 9.81 times that h, or that distance. What was that? That's 0.5 meters, right? 0.5 plus. Okay, so here's where I'm going to account for this plus. Instead of putting plus negative all this, I'm just going to subtract it. I'm just going to put the minus sign up front now. Just want to make sure I didn't double up any minus signs. Minus mu k, our coefficient of friction, that's 0.450 times mass 1, 2.4 times 9.81. Oh, I'm running out of space. No, I'm not. I can just shrink it down a little bit further, which I will do. Look at that. All right. Times our distance moved, and again, the distance is this thing moves is the same thing as the height, right? This distance is the distance that the friction force acts through, so that's why it's the non-conservative force, and that is 0.500 meters as well. And we're going to divide all this by the mass of the system, which is mass 1 plus mass 2. Okay, so mass 1 is 2.4. I should have been writing 2.40 in there. Plus 1.80. And then, of course, we need to remember to take the square root of the whole thing. So this is our working equation, and this will solve for the final velocity of the system. And I get a grand total of 1.7. Let's see, how many? 1.72 meters per second. That's the final velocity of the system. Right when that mass 2 hits the ground, or right before it hits the ground. Of course, the ground stops it, but that's a different kind of problem. That's a collision right there. Right as it's contacting the ground, it is moving at 1.72 meters per second. And this is all done by accounting for all the various different kinds of mechanical energy in the system. Initial kinetic and potential energy, final kinetic and potential energy, and the non-conservative work that is done by friction. Friction is operating over this distance right here, and that took energy out of the system, which is why it lands at a slower speed or a slower velocity than it would have otherwise if there had been no friction on the system. Okay, so this is a good first example of using non-conservative work in our equations for conservation of energy. 1.72 meters per second is our final velocity, and that's our example. So, thanks for following along. I realize this was kind of a longer video, but I think it's worth it, and we're going to be able to apply this to some other problems later on in the chapter and in the course this year. So, make sure you ask me if you have any questions, and I'll see you on the next one.